Good evening everyone. Welcome to the problem solving session of NPTEL course on IC engines and gas turbines. I am myself Pradeev E. I am one of the TA for this course, and today I will solve some problems related to some basic concepts of IC engines, and then I will move on to auto cycle and diesel cycle problems. This kind of problems I also solved in the last week, and these are some first 3-4 problems I have, some problems which are not covered in the last week. If you have any questions of the previous problems, you can ask now, or I can directly start with the problem. So in this problem we have a 1 liter capacity 4-stroke 4-cylinder SI engine which has a brake thermal efficiency of 30% and indicated power of 40 kilowatt at full load. At half load it has a mechanical efficiency of 65%. Assuming constant mechanical losses, we have to calculate brake power, friction power, mechanical efficiency at full load, and indicated thermal efficiency. If the volume decreases by 8-fold during the compression stroke, calculate the clearance volume. So you can start with the problem. Participants can mute yourself. When you have questions, you can unmute and you can ask. Thank you. So we have here we have brake thermal efficiency VTE of 30%, that is I write it as 0.3, and indicated power is 40 kilowatt. Indicated power is so this is at full load. So I write this as full. F means full. Then we have mechanical efficiency at part load. I write it as P, which is 0.65. Okay, part load is half load here, so that is 0.65 or 65%. Assuming constant mechanical losses, we can calculate brake power, friction power, and mechanical efficiency at full load. So when we have 40 kilowatt indicated power, the assume brake power full represents full load output, brake output. This will be indicated power at full load minus friction power. Friction power, since they have said that assuming constant mechanical losses, that means friction power at full load and part load will be the same. Now we have brake power at part load is equal to indicated power at part load minus friction power. And we know based on this relation, mechanical efficiency at part load relation, that is this is brake power at part load divided by indicated power at part load. And using this 1 and 2, we can write friction power. We can take friction power common, and then we will have indicated power of full load minus brake power of full load is equal to indicated power of part load minus brake power of part load. Now using equation 3, so mechanical efficiency is given as 0.65, so we know indicated power at part load is equal to I would write brake power at part load is equal to 0.65 times the indicated power at part load. So we can substitute this in equation. This I write it as equation 4. So substituting in 4, we have indicated power full load minus brake power at full load is equal to I think it is better to write in terms of brake power. So this will be indicated power at part load is equal to brake power at part load divided by 0.65. So we have brake power at part load by 0.65 minus brake power at part load. So I would take brake power at part load common, and then we have 1 by 0.65 minus 1. On the left hand side we have indicated power as 40 kilowatt minus brake power at full load equal to brake power at part load into, you can solve this. Now we know the relation between brake power at full load and part load, that is part load is half load, so that means brake power at part load should be 1 by 2 times of brake power at full load. So using this we can substitute and then get 40 minus brake power at full load is equal to, we have 1 by 2 brake power at full load into 0.5385, which is Can someone solve this? So we have 31.51 kilowatt. So this is the brake power at full load. Now we can calculate friction power. So this means friction power is equal to indicated power at full load minus brake power at full load. This is 40 minus 31.51. This is 8.49 kilowatt. I didn't mention it here. Now the third one is mechanical efficiency at full load. Eta m full load is equal to brake power at full load by indicated power at full load. So that is brake power is 31.51 and indicated power is 40. So we will get the mechanical efficiency. So that is 78.78%. So we have found the friction power, mechanical efficiency at full load. Now we can calculate the indicated thermal efficiency. Indicated thermal efficiency is can be written. So indicated thermal efficiency is the indicated power divided by fuel power. I would write m dot f into CV, and we have brake thermal efficiency as brake power divided by fuel power, so that is m dot f into CV. Using these two, here we know the brake thermal efficiency, that is given as 30%, so this is 0.3, so that means m dot f into CV is equal to so this is at a full load, right? 30%, yeah, at a full load condition. Anyway, we will calculate the indicated efficiency also at full load. So m dot f into CV is brake power divided by 0.3. Now substituting this in the indicated thermal efficiency equation, we have eta ite is equal to indicated power, we know that it is 40 kilowatt divided by brake power by 0.3. So we know brake power is 31.51 divided by 0.3. So we have 105.03. So this is the fuel power. Substituting here, now substituting the fuel power here, we know can calculate the indicated thermal efficiency. So that is 38.1%. If the volume decreases by 8-fold during the compression stroke, calculate the clearance volume. So that means we have volume at BDC, and we have volume at TDC. They say the volume at TDC is 8 times decreased when compared to volume at BDC. So that means volume at TDC is volume at BDC by 8. Now volume at BDC is the total volume, that is V stroke plus VC or V BDC, or I write V total. So this is 8 into V at TDC. So volume at TDC is the clearance volume, VC. So we need to calculate the compression ratio, if I am not wrong. Calculate the clearance volume. Okay, we have to calculate the clearance volume. So clearance volume VC is equal to V BDC Vs plus Vc by 8. It was given the engine is a 1 liter cubic capacity engine, so that means Vs is known as 1 liter. So we can substitute in this equation and we can get the volume, clearance volume. So that would be Vc equal to 1 plus Vc by 8. Then we put 8 Vc is equal to 1 plus Vc. It will become 7 Vc is equal to 1. So Vc equal to 1 by 7 liters, or this is 1.142 liters. Is this problem clear? I would do a recap of this problem. We were given an engine of 1 liter cubic capacity, which is a 4-stroke and 4-cylinder, has a 4-cylinder SI engine, has a brake thermal efficiency of 30% and indicated power of 40% at full load, and at half load the mechanical efficiency is given as 65%, Assuming the constant mechanical losses, we have to calculate brake power, friction power, mechanical efficiency at full load, indicated thermal efficiency, and if the volume decreases by 8-fold during the compression stroke, we have to calculate the clearance volume. So we started with writing the equation for the values, and equation for brake power for full load. Brake power for full load is given by equation 1, which is indicated power at full load minus friction power. Since friction power is given to be same, or the mechanical losses can be assumed constant, we need not write friction power at full load and friction power at part load differently, both are same. In equation 2, we have written the brake power indicated power relation for part load, and in equation 3 we have mechanical efficiency for at part load is given by brake power at part load by indicated power at part load, and using these equations we can calculate indicated power as brake power by 0.65 or brake power by mechanical efficiency. Then using some basic algebra, we were able to calculate brake power at full load at 35.51 kilowatt. Then we using brake power at full load, and we know indicated power at full load is already given, so using these two we have calculated friction power as 8.49 kilowatt, and we have given the mechanical efficiency. We can calculate the mechanical efficiency using brake power and indicated power, which turn out to be the 78.78 at full load. Then we calculated the indicated thermal efficiency using the relation, so we needed the fuel power. So since the brake thermal efficiency at full load is given and brake power is calculated, we have calculated the fuel power as 105.03 kilowatt, and using this we have calculated indicated thermal efficiency as 38.1%. And we were told that during compression the volume in-cylinder volume decreases by 8-fold. So using this we calculated the clearance volume is 0.143 liters, as the total volume or the sub volume is 1 liter as given in the problem. If you have any questions, I can answer now, or I can move on to the next problem. Okay, moving on, we have in the next problem we have a 4-stroke petrol engine at full load delivering 50 kilowatt. It requires 8.5 kilowatt to rotate it without load at the same speed. So that means friction power is 8.5 kilowatt. Find its mechanical efficiency at full load, half load and quarter load. Also find out the volume of the fuel consumed per second at full load if the brake thermal efficiency is 25%, given that the calorific value of the fuel is 42 megajoules per kg and specific gravity of petrol is 0.75. Estimate the indicated thermal efficiency. So we are given that the brake power of the engine at full load is 50 kilowatt, and friction power, since generally we can assume the friction power is constant throughout all the load. Friction power is predominantly a function of speed, so unless stated we can assume that friction power is constant for a particular speed for all the loads. So here the friction power for that speed is given as 8.5 kilowatt. We have to find the mechanical efficiency at full load, part half load and quarter load. So at full load, mechanical efficiency at full load is brake power at full load divided by indicated power at full load. So that means brake power at full load divided by brake power at full load plus friction power. So mechanical efficiency is 50 divided by 50 plus 8.5. So this is 85.47%. Now if you calculate mechanical efficiency at half load, I write it as H. This we have 0.5 of brake power at full load divided by 0.5 brake power full load plus friction power. So that would be 25 by 25 plus 8.5. So that is 74.6%. Similarly, mechanical efficiency at quarter load will be 0.25 brake power at full load divided by 0.25 brake power at full load plus friction power. It should be 12.5 divided by 12.5 plus 8.5. So this is 59.52%. Now we have to find the volume of the fuel that is consumed per second at full load, and brake thermal efficiency is given as 25%. So using this, we know it is brake power divided by m dot f into cv. So 0.25 is equal to brake power at so these are given at full load conditions. This is full load condition, brake power at full load, and m dot f at full load. So 0.25 is brake power at full load is 50 kilowatt. I would write everything in SI units divided by m dot f full load into calorific value. So calorific value is given as 42 megajoules, so that is 42 into 10 power 6 joules per kg. Now I can calculate m dot f at full load. So that is 4.762 into 10 power minus 3 kg per second. The specific gravity of petrol is given as Sg is equal to 0.75. So that means the density of petrol is 0.75 gram per cc. We want to know the volume flow rate per second, so this can also be written as 750 kg per meter cube. So if I want to find the volumetric flow rate of the fuel, this is m dot f divided by rho, then so this is 4.762 into 10 power minus 3 divided by 750 meter cube per second. So this is 6.35 into 10 power minus 6 meter cube per second, or I can write 6.35 cc per second. Is this problem clear? If you have any questions, you can ask now. Okay, I can. If there are no questions, I will move on. This problem, indicated thermal efficiency of a 4-stroke engine is given as 32% and its mechanical efficiency is 78%. The fuel consumption rate is 20 kg per hour, running at a fixed speed. The brake mean pressure developed is 6 bar, and the mean piston speed is 12 meter per second. Assuming it to be a single cylinder square engine, calculate the crank radius and speed of the engine. Take CVS 42,000 kilojoule per kg. So indicated thermal efficiency ITE is 32%. So this is indicated power divided by fuel power, which is m dot f into CV. Mechanical efficiency is given as 0.78. So this is brake power by indicated power. The fuel consumption rate m dot f is given as 20 kg per hour, or this is 20 by 3600 kilogram per second. The brake mean pressure developed is 6 bar, so that means BMEP is 6 bar. And the mean piston speed is is 12 meter per second. Assuming to be a single cylinder square engine, so that means if it is a square engine, we have bore is equal to stroke. CV is 42,000 into 10 power 6 joule per kg. Here the BMEP is given, so from BMEP we can calculate BMEP will have a relation between the brake power, brake torque, the BMEP will have a relation between brake power, speed and volume. So if you write brake power BMEP into L into A into N by 6G into small n. So here the small n is, since it is a 4-stroke engine, we have this small n as the n comes here into n. N is 2 for a 4-stroke engine. Now brake power is also not given. I think using the m dot f and calorific value, we can calculate the fuel power, which will give the indicated power, and then using mechanical efficiency we can calculate the brake power. So then if you put brake power and BMEP in this relation, you will get relationship between L, A and N, that is speed and the dimensions. We have been told that it is the square engine, so that means bore is equal to stroke. Using that relation and the speed relation, we will be able to find the crank radius and speed of the engine. So first I will start with calculating the fuel power. So m dot f into cv is 20 by 3600 into 42 into 10 power 6 joule per kg. So that is so this is 233.3 kilowatt. Now using the indicator thermal efficiency equation, I can calculate indicated power is 0.32 into fuel power. So that is 0.32 into 233.3. So this is 74.67 kilowatt. Now using mechanical efficiency, brake power is 0.78 of indicated power. So we have 0.78 into indicated power, which is 74.67. So this turns out to be 58.24 kilowatt. So now using this brake power and substituting in that this equation 1, we will be okay. So brake power is I will write the equation again. BMEP is equal brake power is equal to BMEP into L into A into N by 60 into small n. So here brake power is 58.24. Writing everything in SI units, I will have converting kilowatt to watts, I will have 10 power 3, and BMEP is said to be 6 bar, so that is 6 into 10 power 5 pascals in SI units. So L is stroke length, so I would write in L into area is pi by 4 d square. So since I would write d square into n divided by 60 into n. So the small n is 2 since it is a 4-stroke engine. Now we know that L is equal to d. I can have everything in terms of d, and we know mean piston speed is equal to 12 meter per second. So that is 2 Ln by 60 is 12. Right, so Ln is equal to, I would have 12 into 60 by 2. This is 360. I can substitute this in the equation 2. Equation 2 is 2 will become 58.24 into 10 power 3 is equal to 6 into 10 power 5 into Ln I am substituting as 360 into pi by 4 d square divided by 120. So with this I can calculate d. I would write d square first. D square is this is 0.0412. That means d is equal to 0.203 meters. So that is the bore or stroke of the, so d is equal to L equal to 203 mm. So in the question it was asked as crank radius. So crank radius. R is equal to L by 2, which is 203 by 2, which is 101.5 mm. And we were asked to calculate the speed of the engine. So we had 12 meters per second, main piston speed as 12 meters per second, which is 2 ln by 60. So with this we have n is equal to 12 into 60 divided by 2 into L. So L is 203. So we have 1773.4 rpm. We have calculated R as well, the speed of the engine. You have any questions with the problem? Okay, moving on. I have some problems using autocycle, so I would first introduce the autocycle briefly. I hope this would be covered in the regular weekly class video, so I will just briefly explain this. So in the PV plot, the autocycle can be plotted. So initially we have gas inside a cylinder at low pressure and high volume, and initially that is compressed. We say this state as 1, that is compressed adiabatically, isentropic adiabatic. With isentropic adiabatic compression we compress it to the second state 2. So that will trace a path like this, and then we have a constant volume heat addition between 2 and 3, and that means that will be a vertical line in the PV plot. And then we have isentropic expansion, again that will trace a similar path like the compression, which will end at 4, and then we have a constant volume heat rejection, and then it comes back to its original state at 1. So 1 to 2 is isentropic compression, 2 to 3 is constant volume heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is constant volume heat rejection. So I hope you will be familiar with the assumptions of the air standard cycle. So we assume all processes are reversible. And we assume the components doesn't change, components of the gas. There is no friction between the piston and the surfaces liner, and there is no heat transfer at finite temperature difference and so on. So with all these assumptions and these processes, we will get the efficiency of the autocycle as 1 minus 1 by R power gamma minus 1. Here R is compression ratio, compression ratio can be written as volume at 1 by volume at 2, or volume before compression and divided by volume after compression, or volume at 4 by volume at 3. So that is volume after expansion to volume before expansion. So these are the basics of the Otto cycle. If you have any questions about the Otto cycle, we can discuss now. If there are no questions, I will move on to the problems. An engine working on Otto cycle has the following conditions. Pressure at the beginning of compression is 1 bar, pressure at the end of compression is 11 bar. Calculate the compression ratio and as standard efficiency of the engine. Assume gamma is 1.4. So from the plot, P1 is given as 1 bar and P2 is given as 11 bar. We need to calculate the compression ratio, which is V1 by V2. So using the relation during isentropic compression or expansion, we know PV power n is PV power gamma is equal to constant. So that means P1 V1 power gamma is equal to P2 V2 power gamma. Now if you want V1 by V2, we will have P2 by P1 power 1 by gamma. So writing this in terms of pressure, we have P2 by P1 power 1 by gamma. So that is 11 power 1 by 1.4. So this is 5.54. So this is the compression ratio, and if you want to calculate the air standard efficiency, we have 1 minus 1 power 1 by 1 power r power gamma minus 1. So that is 1 minus 1 by 5.54 power 0.4. So this is 0.4958 or 49.58% efficient. Is this problem clear? Participants can unmute yourself. If you have any questions, you can unmute yourself and ask.
2 weeks ಅಂತ ಇದೆ.
Moving on to the next problem. In an engine working on ideal Otto cycle, the temperature at the beginning and end of the compression are given as 50 degrees Celsius and 370 degrees Celsius. I have to find the compression ratio and air standard efficiency of the engine. So temperature at state T1 is given as 50 degrees Celsius. So that is 50 plus 273 Kelvin. Which is 323 Kelvin. Similarly, T2 is 373 degrees Celsius. Which is 646 Kelvin. Now again using relations like this, PV power gamma, and using ideal state equation, we should be able to find the volume ratio when the temperature ratio is given. We had V1 by V2 is equal to P2 by P1 power 1 by gamma. Using ideal state equation, we have PV equal to mRT, which means PV power T by T is equal to constant. That means P1 V1 by T1 is equal to P2 V2 by T2. Using the previous relation, we can write P2 by P1 is V1 by V2 power gamma. Now substituting this relation in the ideal state equation relation, we will get relationship between V1 and volume and temperature. So we have P2 by P1 V2 by V1 is equal to T2 by T1. So P2 by P1 is V1 by V2 power gamma, and we have V2 by V1 is equal to T2 by T1. So that is V1 by V2 power gamma V1 by V2 power minus 1 is equal to T2 by T1. So that is V1 by V2 gamma minus 1 is equal to T2 by T1. And V1 by V2 is equal to T2 by T1 power 1 by gamma minus 1. That is 646 by 323 power 1 by 0.4. So compression ratio is V1 by V2, which is 5.65 is the compression ratio. When we want water cycle efficiency, we use this relation 1 by R power gamma minus 1. That is 1 minus 1 by 5.65 power 0.4. So this is 49.97%. Any questions with this problem?
So gamma you took as a standard value, is it?
Yes.
0.4?
So yeah, gamma, if it is not given, you can take it as 1.4, because gamma of air at atmospheric temperature is generally 1.4.
Okay, thanks. Yeah.
Any other questions? Okay, I will move on to the next problem. In an Otto cycle, air at 17 degrees Celsius and 1 bar is compressed adiabatically until the pressure is 15 bar. So that means T1 is 17 degrees Celsius, which is 17 plus 17 plus 273, that is 290 Kelvin. P1 is given as 1 bar and P2, that is pressure after compression, is 15 bar. Heat is added at constant volume until the pressure increases to 40 bar. So that is P3 is 40 bar. Calculate the as standard efficiency, the compression ratio, and the mean effective pressure for the cycle. Assume CV is 0.717 kJ per kg Kelvin and R is 8.314 kJ per kilomole Kelvin. Now first we can start with calculating the compression ratio. So compression ratio is V1 by V2. We have already found the relation V1 by V2 is P2 by P1 power 1 by gamma, yes, 1 by gamma. So since gamma is not given, we can also calculate gamma using these given parameters, that is CV and R. So since R is given in universal gas constant, we need to calculate characteristic gas constant, which is R is R bar by molecular weight, which will be 8.314 into 10 power 3 having in SI units divided by 29. So molecular weight of air is 29. So this we will have 287 joule per kg Kelvin. Now CV is given, so Cp is Cv plus R, so that is 717 plus 287. This is 1004 joule per kg Kelvin. Now gamma is Cp by Cv, which is 1004 divided by Cv is 717, which is 1.4003. So we approximate it to 1.4. Now we can calculate the compression ratio as P2 by P1 power 1 by gamma. P2 is 15 bar divided by P1 is 1 bar, power 1 by gamma is 1 by 1.4. So we have 6.92 as the compression ratio. Using someone has a question? As standard efficiency for outer cycle is 1 minus 1 by R power gamma minus 1. So substituting the values of R as 6.92 and gamma as 1.4, we can get the as standard efficiency. So that is 53.87%. We have obtained the compression ratio and as standard efficiency. Now we need to calculate the mean effective pressure for the cycle. So mean effective pressure is work done per cycle divided by displacement volume. I think we will not be able to use this. Yeah, volume can be found by using the conditions at the first state. So we have temperature and pressure given. Using that, we will be able to calculate the specific volume, and with that and the work done per cycle, we will be able to find the mean effective pressure. So to calculate the work done per cycle, we can make use of the efficiency relation and the heat addition inputs. So we were told that heat was added until 40 bar, so heat was added from 15 bar till 40 bar. So we had P3 as 40 bar. We can calculate the temperature at state 2 and state 3, and then using the temperature difference and CV value, we will be able to calculate the joules of heat that is added, and with the Otto cycle efficiency and the heat input, we will be able to calculate the work done. So now we can calculate T2. We had the temperature relationship here. So T2 by T1 is here. T2 by T1 is V1 by V2 power gamma minus 1. So V1 by V2 is a compression ratio, that is 6.92 whole power 0.4. So T2 into T1. So T1, we know that it is 290 Kelvin, right? 17 plus 273. into power 0.4 into 290. So we would have T2 is 628.7 Kelvin. Now we need to calculate T3. Using the relation PV is proportional to, or PV by temperature is equal to constant. This is ideal case relation. So for any kind of process, any kind of closed process, when there is no change in mass, this equation holds good. So writing this for state 2 and 3, we have P2 V2 by T2 is equal to P3 by T3. We know the heat addition happens between state 2 and 3, so that means volume at 2 and 3, that is V2 and V3 are the same, so we can strike it off. We had 2 here, so these 2 goes off. Now T3 is P3 by P2 into T2. So T2 is 628.7 Kelvin into P3 is 40 bar and P2 is 15 bar. So this is 1676.5 Kelvin. Now we can calculate the heat added. QH is M or CV into T3 minus T2. So that is 717 into 1676.5 minus 628.7 Kelvin. So heat added is 751 272.6 joules per kg. So since we had a CV as joules per kg Kelvin, and we had multiplied only with the temperature and not the mass. We have found the heat added per cycle for unit for 1 kg of the air in the cycle. Now we know we have to find the displacement. So at the initial state we can calculate P1 as we had P1 V1 equal to mRT1, or P1 volume 1 is equal to, so this is specific volume is RT1. Pressure at first state is given as 1 bar, so that is 10 power 5 V1 is equal to R is we calculated it as 287 and temperature is 290. So this is 287 into 290. So that means V1 is 0.8323 meter cube per kg. So this is V1. When we want to calculate the mean effective pressure, we have displacement volume, so that is V1 minus V2. Using compression ratio we can get the relationship. Compression ratio is V2 by V1 minus V2. So this is calculated is 6.92. Now we can calculate V2 as so 7.92 V2 is equal to 6.92 V1. I think so compression ratio, okay, sorry, I think I put the other way. Sorry. Compression ratio is V1 by V2, yes. So we have V2 is V1 by 6.92. So that is 0.8323 by 6.92. Which is 0.1203 meter cube per kg. So displacement volume, or I write it as V displacement equal to V1 minus V2, that is 0.8323 minus 0.1203. This is 0.712 meter cube per kg. Now we have mean effective pressure as work done per cycle divided by displacement volume. So work done per cycle we have calculated it as okay, we had only QH, so work done is equal to QH into eta auto, which is 751,272.6 into auto cycle efficiency, that is 0.5387. So we have 404,710 joule per kg. So substituting here we have 404,710 joule per kg divided by displacement volume is 0.712 meter cube per kg. So kg get cancelled, we have joule per meter cube, which is a general notation terms we use for the MEP, work done by displacement volume. So this turns out to be 568,412.9 pascals. So joule per meter cube will become pascals. So this is 5.68 bar. So we have calculated the mean effective pressure as 5.68 bar. Do you have any questions with the problem?
Why the weight of air is taken 29? It to be 30, no? Because the weight of oxygen and nitrogen is 14 and 14 and 15, and the summation of these two are 30.
Yeah, molecular weight of nitrogen is 28, right? And molecular weight of oxygen is 32. I don't remember the exact value finally. Maybe it is 28.9 or 29.9. But anyway, even if it is 30, this value, I remember this 287 is almost the same, and this CP is also around 1005. Now we have got 1004, and anyway these will affect only the gamma value that we have taken. Gamma is 1.4, which is a standard value, so a small change in this will not affect here, but you may be right. If the molecular weight is 29.9 or 30, you can use the same value. Any other questions?
No, sir.
Okay. In the next problem, we have a SA engine where the fuel is supplied, which has a calorific value of 42,000 kilojoule per kg. The pressure in the cylinder at 30% and 70% of the compression stroke are 1.3 bar and 2.6 bar respectively. Assuming that the compression follows the law PV power 1.3 is equal to constant, find the compression ratio. If the relative efficiency of the engine compared to the air standard efficiency is 50%, calculate the fuel consumption in kilogram per kilowatt hour. So we are given the calorific value of the fuel is 42,000, or I can write it as 42 into 10 power 6 joule per kg. The pressure at 30% stroke and 70% stroke is given. So P at 0.3 S and P as 0.7 S given as 1.3 bar and 2.6 bar. Assuming that the compression follows PV power 1.3 is equal to constant, find the compression ratio if the relative efficiency of the engine is with the air standard cycle. So that means efficiency is equal to 0.5 times the auto efficiency, or actual efficiency is 0.5 times the auto cycle efficiency. We have to calculate the fuel consumption in gram per kilowatt hour. First we need to calculate the compression ratio. So we know that this compression, during compression, follows a curve like this. We have 1 and 2. So this is V1, this is V2. 30% compression, 30% stroke represents some point here and 70% represents here. So 30% means, so this is 0.3 times V1 minus V2, and this represents 0.7 times V1 minus V2. So using the pressure and volume relation, and we can try substituting these values, and then we will be able to find the values V1 and V2. So the pressure and this relation we had here, V1 by V2 is P2 by P1 power 1 by gamma. So was the initial pressure given? No. So we have V1 by V2 is equal to P2 by P1 1 by gamma. 1 by gamma, yes. So here V1 is, we can assume V1 is 30% stroke. So at 30% stroke we had 0.3 V1 minus V2. So, and second state is 70% stroke, that is 0.7 times V1 minus V3. But actually the volume at 30% stroke is not this one. So volume at here, so I will write volume at 0.3 stroke divided volume at 0.7 stroke is equal to P2 by P1, which is 2.6 by 1.3. This is 1 by, okay, gamma. We have to consider PV power gamma 1.3 is equal to constant. We have PV power, we have 1 by 2.6 by 1.3 power 1 by 1.3. So this is 1.704. So can we write volume at 0.3 stroke is equal to 0.3 times V1 minus V2 we come from here, from the towards from the right. So we have V1 minus 0.3 times V1 minus V2. So now if we have 0% stroke, that means this term will become 0. We will have V1. So 0% stroke is at BDC, so we will have the maximum volume, that is V1. Now if you have 100% stroke, this 0.3 will become 1. So we will have V1 minus V1, V1 and V1 will get cancelled, and then we will have minus of minus V2, so that is V2. Sorry. I hope this thing is clear to you. So I write V as sub x into stroke V1 minus x into V1 minus V2. So if x equal to 0%, we have v0. Yes, so 0% stroke is, we should be getting v1, right? So this is v1 minus 0 into v1 minus v2, so we will have v1, right? So at 0 stroke we have the full volume v1, and if x equal to 100%, we have v100 stroke is equal to or okay, we have v1 minus 1.0. so 100% is for x equal to x will be 1.0, v1 minus v2, this will be v1 minus v1 plus v2. So volume at 100% stroke is equal to v2. Okay, so this way we can write this relation like this. So volume at 30% stroke is v1 minus 0.3 v1 minus v2. So v.3 stroke is equal to v1 minus 0.3 v1 minus v2. This will be like 0.7 v1, right, plus 0.3 v2. Similarly, volume at 70% stroke is volume at v1 minus 0.7 volume 1 minus volume 2. We will have 0.3 v1 plus 0.7 v2. We had the relationship here. We had v.3 stroke and volume at 70% stroke is 1.704. That means 0.7 v1 plus 0.3 v2 divided by 0.3 v1 plus 0.7 v2 is equal to 1.704. I think we will need another relation to find this. I think the initial volume pressure at the initial volume V1 should be given. Otherwise, anyone has an idea how to solve this problem? Yeah, Chaudhary Manish. You can unmute and you can talk. Chaudhary Manish, can you unmute yourself and you can speak up?
Yes, sir.
Yes.
Yes, sir.
Yeah, you raised a hand, right? You have anything to say?
No, sir. So, sir,
Okay.
it's pressed by mistakenly,
Okay,
sir.
no problem.
So the 1.704, that relation is given, right? Or
Yes. So that we have calculated using the pressure volume relation.
oh, sorry, yeah. Mhm. Yeah, thanks.
I think for the compression ratio we need only the relationship between we want the ratio between V1 and V2, right? So compression ratio is V1 by V2. We don't need to find the absolute values of V1 and V2. So then I think we'll be able to solve. So we have this equation 1. So 1, we divide 1 by say V2, then we have 0.7 V1 by V2. I write V1 by V2 as compression ratio plus 0.3 equal to 1.704, then 0.3 of compression ratio plus 0.7, right? Then we have compression 0.7 minus 1.704 into 0.3 of compression ratio. This is equal to 1.704 into 0.7 minus 0.3. Can calculate the compression ratio. 0.704 into 0.7 minus 0.3. So we have 4.73 as compression ratio. The compression ratio is decreasing for every problem. So it's 4.73. We have Otto cycle efficiency as 1 minus 1 by r power gamma minus 1, or here it is n minus 1, since we were being told that it follows the relation PV power 1.3 is constant. So we have 1 minus 1 by 4.73 power 0.3 . So we have 37.26%. And so with the relative efficiency is given with respect to air standard cycle is 50%. So that means actual efficiency is 0.5 times the Otto efficiency. So that will be 0.5 into 37.26. So that is 18.63%. Now we know the actual efficiency. We know we have to find the fuel consumption in terms of gram per kilowatt hour or kg per kilowatt hour. For finding this, we have calorific value as 42,000 kilojoules per kg, and we also have efficiency. So we have brake thermal efficiency is given as that is calculated as that is value, this 18.68, that is the actual efficiency. This is given by brake power by m dot f into CV. This turns out to be 0.1863, right? So brake power is equal to m dot f into calorific value is 42 into 10 power 6, if I am not wrong. Yeah, 42,000, which in SI units we will have 42 into 10 power 6 into 0.1863. Now we need to calculate the specific fuel consumption. That means m dot f divided by brake power will be 1 by all this, 42 into 10 power 6 into 0.1863. That is 1.278 into 10 power minus 7. So this units is for m dot f we will have kg per second, and for brake power we will have joules per second. right? So now we need to, so this will become kg per joules. So this is 1.278 into 10 power minus 7 kilogram per joules. In the question we were asked to find kilogram per kilowatt hour. So 1 kilowatt hour is equal to 10 power 3 watt hour, which is 10 power 3 watts into 3600 seconds, right? So then now this will become 10 3600 into 10 power 3 watt seconds, so that will become joule. So that is 3.6 into 10 power 6 joules. Now writing this relation, we have m dot f by brake power is 1.278 into 10 power minus 7 into 3.6 into 10 power 6 kilogram per kilowatt hour. So that is 0.46 kg per kilowatt hour. Any questions with the problem? Okay, then I will move on to the next problem. We have a Otto cycle, engine working in Otto cycle with a cylinder diameter of 200 mm and stroke of 250 mm. The clearance volume is given as 1570 cc. We have to find the as standard efficiency. We can assume CPS 1004, CVS 0.717 for air. So we know this volume cylinder. The total volume is given as the stroke volume is pi by 4 d square into L. So that is pi by 4 into since the clearance volume is given in cc, I would write everything in centimeters, so I will directly get the stroke volume in cc. So that is d square is 20 centimeters square into length is 25 centimeters, since it is 250 mm. So I will have 7854 cc. Clearance volume is given as 1570. So we will have compression ratio as Vs plus Vc by Vc. So compression ratio is 7854 plus 1570 divided by 1570. So this is 6. We have as standard efficiency gamma is equal to Cp by Cv, which is 1.004 by 0.717, which will be 1.4. Now as standard efficiency eta auto is 1 minus 1 by compression ratio power gamma minus 1, so that will be 1 minus 1 by 6 power gamma minus 1 is 0.4. So this is 51.16%. I hope this problem is straightforward. So I'll move on to the next problem. In an SI engine working in an ideal Otto cycle, the compression ratio is 5.5. The pressure and temperature at the beginning of compression are 1 bar and 27 degrees Celsius. The peak pressure is 30 bar. Determine the pressure and temperature at the salient point. So the air standard efficiency and the mean effective pressure. Assume ratio of specific heats to be 1.4 for air. So we need to calculate the pressure and temperature at each salient point. So that is 0.1, 2, 3 and 4. Pressure at 1 is given as 1 bar. T1 is given as 27 degrees Celsius, which is 27 plus 273, which is 300 Kelvin. Yes, 300 Kelvin. Compression ratio is given as 5.5. We know, and peak pressure is also given as 30 bar. So that is P3 is 30 bar. From relation we know P2 by P1 is P2 by P1 is V1 by V2 by power gamma. V1 by V2 power gamma, that is compression ratio power gamma. Compression ratio is 5.5, power gamma is 1.4. So P2 will become 1 into 5.5 power 1.4. So this is 10.87 bar. Now we know the pressure at second state. We need to calculate the temperature at second state. So we have the relation T2 by T1 is we use it here. T2 by T1 is V1 by V2 power gamma minus 1. V1 by V2 power gamma minus 1. So this is again compression ratio power gamma minus 1. Compression ratio is 5.5, power gamma minus 1 is 0.4. So T2 will be 300 Kelvin into 5.5 power 0.4. So this becomes 593.3 Kelvin. Now P3 is given as 30 bar. We can calculate T3. So for this we use the relation P2 V2 by T2 is equal to P3 V3 by T3. Here between 2 and 3 the volume is same, so the volume get cancelled. We will have T3 as T2 into P3 by P2, which is 593.3 into P3 is 30 bar and P2 is 10.87 bar. So we can calculate T3. So this becomes 1637.4 Kelvin. We have calculated till 0.3, pressure and temperature at 0.2 and 3. Now we can calculate at 0.4. So for this we can again use the same relationship. So we had P2 by P1 as compression ratio, so now we will have P3 by P4 will be same compression ratio power gamma. So that means P4 is P3 by compression ratio power gamma. So that is, we had P3 as 30 bar divided by compression ratio is 5.5 power gamma 1.4. So we know P4. Which is 2.76 bar. Again, using this temperature relation, we can calculate T4. So that would be T4 is equal to, we can use the relation between T4 and T1 because that volume are same. So we have T4 as T1 into P4 by P1. So this is at T1 it was 300 Kelvin into P4 is 2.76 bar, and at P1 is 1 bar. So we have T4 as 828 Kelvin. So this way we have found the pressure temperature at all the points. Now we can find the air standard efficiency and mean effective pressure. For air standard efficiency, compression ratio is enough, is sufficient to find. So eta O2 is equal to 1 minus 1 by compression ratio power gamma minus 1. So this is 1 by 1 by 5.5 into 0.4. So this is 49.43%. Now we need to calculate mean effective pressure, which is work done per cycle by displacement volume. Using the as we calculated earlier, QH is heat added is CV into T3 minus T1 or T2, which is 717 into T3 is 1637 and T2 is 593. So we have 548 joule per kilogram. That means work done will be motorcycle efficiency into QH, which will be 0.4943 into QH is 548. So we have 370,007 joules per kg. Similarly, we can find the displacement volume. Displacement volume is equal to V1 minus V2. V1 can be calculated using PV equal to RT, at state 1. V is equal to, we calculated R earlier. R for air is 287. Yeah, R for air is 287. 287 into temperature at first state is 300 Kelvin by pressure at first stage, which is 10 power 5, 10 power 5, 1 bar, which is 10 power 5 pascals. So we have 0.861 meter cube per kg. We had compression ratio, which is V1 by V2 is 5.5, which means V2 is 0.861 by 5.5. So this is 0.156 meter cube per kg. Now V displacement is equal to V1 minus V2, which is 0.861 minus 0.156. So this is 0.705 meter cube per kg. Now mean effective pressure is work done per cycle, which is 748,548 divided by displacement volume, which is 0.705. So this turns out to be 1061770 Pascal. So this will be 10.61 bar. Do you have any questions with the problem?
Hi.
Yes.
This 748, this MEP should be the work done, right? That's it, 370007.
Work done is yes, sorry.
Okay.
Give it the heat input.
Yeah, 18 to
So MEP is work done, so then is 370007 divided by displacement volume is 0.705. Yeah, right. Which is 524,832, which is 5.24 bar. Yeah, thank you for pointing. Any other questions? Okay, I move on to the next problem. Gas engine operating on the ideal Otto cycle has a compression ratio of 6:1. The pressure and temperature at the commencement of the compression are 1 bar and 27 degrees Celsius. Heat added during the constant volume combustion process is 1170 kJ per kg. Determine the peak pressure and temperature, work output per kg of air, and air standard efficiency. So compression ratio is given as 6, and P1 is 1 bar, and P2 is 27 degrees Celsius, which is 300 Kelvin. Heat added is 1170 kilojoule per kg. We know the compression ratio, so we can calculate P2 by P1, which is compression ratio power gamma minus 1, as we have seen earlier. So this is 6 power 0.4, and P2 is 1 bar into 6 power 0.4. If someone is following calculating yourself, you can also tell the answer by unmuting yourself or by in the chat window. So this will make the session more lively.
This 300 Kelvin is T1, correct?
Yes, yes. Yeah. So can you calculate pressure at second state P2? I've calculated it as 2.05 bar. Now we can calculate T2, which is T1 into what did we had? Yeah, compression ratio power gamma minus 1. So compression ratio power gamma minus 1. So this is 300 into 6 power 0.4. I think here it is gamma, right? P2 by P1 is yeah, it's not gamma minus 1, it is 1.4. So this is 12.3 bar. So this is 614 Kelvin. So this is T2. We have given the heat addition, so we can calculate T3. So how do we calculate this? QH is CV into T3 minus T2. So QH is given as 1170 into 10 power 3 to have it in SI units, that is joule per kg, is equal to CV is 0.717 kilojoule, so it is 717 joule per kg Kelvin into T3 minus T2. T2 is 614 Kelvin. So T3 can be calculated as 1170 into 10 power 3 divided by 717 plus 614. This is 2246 Kelvin. So we have to calculate the peak pressure. You can use the relation P2 V2 by T2 equal to P3 V3 by T3. Here volume before and after heat addition is same because it is a constant volume heat addition. Then we will have P3 as P2 into T3 by T2. So P2 is 12.3 bar into T3 is 2246 divided by T2 is 614 Kelvin. So we will have P3 as I get 45 bar. So peak pressure is calculated as 43 bar. and peak temperature is also calculated, which is 2246 Kelvin. Now work output per gram of air and air standard efficiency has to be calculated. So air standard efficiency is 1 minus 1 by compression ratio power gamma minus 1, which is 1 minus 1 by 6 power 0.4. So this is 51.16%. Now work output is QH into efficiency. So that is efficiency is 0.5116 into QH is 1170.
Not PR.
Sorry,
The symbol you got mistaken, sir.
sorry, the
In the-
symbol compression ratio.
Yes, sir.
Yeah, so in some problems I have taken this as small r. Oh, okay, here it is, efficiency. Okay,
Yes, sir. Yes, sir.
thank you.
That got it. Yes.
So yeah, work done is 1170 into 0.5116. So this is 598.6 kilojoule per kg, because the heat added is kilojoule per kg. Now work output per kg is found of the air standard efficiency is also found. I think that's a problem. Any question with this problem? We have only 6 more minutes, 6 more minutes or 5 more minutes. So I would just brush up the basics of the diesel cycle for now. So in the diesel cycle, similar to the Otto cycle, we have constant isentropic compression represented by 1 and 2, state 1 and 2, which is isentropic compression. And in this in a diesel cycle, the heat added is at constant pressure. So 2 and 3 will have the same pressure. That means it is a horizontal line in a PV diagram. So 2 to 3 is constant pressure heat addition, and 3 to 4 is again isentropic expansion, same as the Otto cycle. So this is represented by 3 and 4. We have isentropic expansion, and 4 to 1 is constant volume heat rejection. So here we have two ratios to be defined. So one is compression ratio, which is volume, which is between volume 1 and volume 2, and we have something called cutoff ratio, which is given by volume 3 by volume 2. So this is volume after heat addition divided by volume before heat addition. Using these two, we can calculate a diesel cycle efficiency. I don't have it at the back of my mind, so I have it here. So eta diesel is given as 1 minus 1 by r power gamma minus 1 divided by 1 by gamma into cutoff ratio power gamma minus 1 by compression ratio minus 1. So maybe we can solve this problem quickly. We have compression ratio or R as 20, and cutoff takes place at 5% of the stroke. So RC is uh, we have this. So 5% of the stroke represents, this is 5% when compared to the total stroke. So we need to find the ratio between V3 and V2. V3 minus V2 is equal to 5%, 5 by 100 of V1 minus V2. Then we will have dividing everything by V2, we will have V3 by V2 is minus 1 is equal to 5 by 100 V1 by V2 minus 1. So this is 1 by 20. V1 by V2 is compression ratio, which is 20. We have 20 minus 1, and this is cutoff ratio minus 1. So cutoff ratio is 19 by 20 plus 1. So this is 1.95. So diesel cycle efficiency is 1 minus 1 by 20 power 0.4 into gamma is 1.4. Cutoff ratio power gamma is 1.95 power gamma is 1.4 minus 1 divided by 20 minus 1. Can someone do this computation? Let me break down this. 1.95 power 1.4. So the numerator is 1.547, and this is 20 power 0.4 into 1.4 into 90. So this is 1 minus 1. Is this right?
Sir, it's mistake in right here. You have written B3 by B2 is equal to RC.
Sorry, in the RC calculation?
Yes, sir. Yes, sir.
Mm-hmm.
It is to be right here, I guess. B1 by B2 in the right hand side.
Right hand side, it is 5 by 100 into V1 by V2 minus 1, right?
Yes, yes, sir.
Yeah.
So RC should be right here
Sorry, RC should be?
in the right hand side, I guess. Given by B2, no?
So,
So B3 by B2 is
hmm,
never RC, no?
so we had V3 minus V2 is 5% of V1 minus V2, right? That is correct, no?
Yes, sir. Just go through third line.
Third line,
First line, second line, third line.
RC minus 1.
Yes.
Yeah. So RC, V3 by V2 is RC, right?
B3 by B2 is RC.
Hmm.
Compression ratio.
No, RC is cutoff ratio.
Okay.
But yeah, I think RC is cutoff ratio.
Okay. Okay. Yes, sir. Yes. Then it's right. Yes, sir. Yes, sir.
1.9 is typical cutoff ratio.
Yes. Then it's right. Sorry, sir.
No problem. Okay. I think if you are not able to find it, I will find and I will
But
explain. Yeah.
the process of doing the answer is right, I guess.
Yeah, seems right, but maybe something we are missing. No problem. I think since it's already 8 o'clock, and if you are able to find it, you can
It is 0.983.
yeah, 0.98.
That is 98.3.
Yeah. That is not possible, right? That's why I didn't
Yeah,
write
that's not possible.
well.
Yeah, that's the efficiency. Yeah.
Yeah, 98% is not possible for this
Yeah.
example.
Mm.
So there is some problem with the calculation.
I did twice.
Yeah. No problem. I would find the proper solution, and I will update in this PDF. You can see in that portal, and also I will explain in the next session in the first few minutes.
So all these things as PDF they will come later on, right? We will be able
It's
to verify, cross check, or
NPTEL has already started to share the PDF.
okay.
Were you able to see it, or should I show you how it is?
No,
Uh,
sir. We have seen.
I think yeah, I can manage it.
Okay. Okay. If you have any questions, I can answer now, or you
Sir,
can.
once
Sir,
show it.
sir,
PDF.
Once show it, yeah.
No time. Yeah.
Okay.
sir, where will we get our PDF?
Yeah,
Yes.
that's
Yes.
what. That's
Yeah.
what.
Yeah. I will show you.
Just show one time.
Can you show one, sir, where to get the
Yes.
PDF
Yes.
from?
I can show you. I can show you. So you have this portal, right? You can see the NPTEL portal on my page. So
Yeah.
here we have week 1, week 2. You would have seen the videos like here, and in the bottom you have problem solving session.
Okay.
Yeah. If you open this, you can click here. It will open a Google link. Google.
Oh yeah. Okay, sir.
Yeah. Week 1, week 2.
Thank you, sir.
Thank you so much, sir.
Yeah. No problem.
Yeah. Thanks a lot.
Okay then. If you don't have any questions, we can close the session and meet in the next class. Thank you, everyone.
Okay, sir. Thank you, sir.
Yeah. Thank you.